Hey everybody, I'm super excited to let you see this presentation. Again, we're not putting all the presentations from the HVACR Symposium up on YouTube, but some of them I just had to share with everybody, and this is a really great one. It's on the topic of thermal imaging. Basically, how do you really apply thermal imaging in the real world? And it's from two of my very favorite people, Kaiser and Bill Spohn, two guys who have helped me out tremendously, two of the best minds in our trade. And obviously Bill knows a lot from the tool side. He's sold a ton of thermal imagers. He's been working with thermal imaging camera technology for a really long time. And then you have Kaiser, who has applied much of this in the field. And so together they kind of have this really great presentation for those of you who want to know more about thermal imaging. So big thanks to them. Big thanks to all of our sponsors, MeasureQuick, ACA, who made the symposium possible. You can still get all of the various presentations by going to hvacrschool.com/symposium. Sign up there and you can still get the virtual ticket. And pretty soon you're going to be able to sign up for next year's symposium too by just keeping an eye out at that link, hvacrschool.com/symposium. But here we go. Kaiser and Bill Spohn talking about thermal imaging applied in the real world.
So we're talking about thermal imaging, and realistically what we want to do here is to increase everybody's comfort level with thermal imaging, because it's kind of one of those things that, okay, we've seen it, we've heard of it, but what the heck do we do? Here, you want to hold on to that? Yep. So what do we do with it? How do we use it? Where do we apply it? What do we know when we look at that image on the screen or on our computer? What are we going to do with that? So that's kind of what we're going to do. Now, this is not like super detailed or anything in here. There's a lot more education if you want to get in-depth in thermal imaging. But we want to talk about some of the practical application of it, some of the basic theory, and highlight some of its uses and the limitations of it. Because like any other tool out there, it's another tool in our toolbox, it has its limitations. And if we don't understand what the limitations are, we can have unrealistic expectations of a tool. Okay? It's like using a wrench that's the wrong size on a nut. We have an expectation that it's going to turn that nut. Well, if it's the wrong size and it just slips and rounds the nut off, we had an expectation it didn't do the job, and now we're either unhappy with the nut or unhappy with the wrench. Makes sense, right? So that's where we want to go with this. Now, thermal imaging is useful for several things, but the biggest thing it's useful for is making a comparison between different points, A and B. Okay? We want to look at two separate things here. We're going to say the temperature on this side versus the temperature on this side, and it makes it a visual because we're very visual people, and it helps us visualize. It also helps our customers visualize these differences. But where thermal imaging really shines is when we're looking at multiple points. All right? We can go A, C, B, C, D, hundreds of points, thousands of different points of temperature comparison on one screen really, really fast. So that's where thermal imaging really shines, is visually comparing two different or multiple different temperatures simultaneously.
And if you set up the cameras correctly,
yes,
it's like a highlighter on the picture of the world of what are you looking for? It'll highlight for you. So it'll drive you to doing the work in the right place rather than having to just kind of shrug your shoulders. Like, there's something wrong here. I don't know what it is. And thermal measurements are the most basic measurement going back, forever. So the temperature measurement is important.
I mean, that's what we do in this industry, is we move heat from point A to point B. Right. And we convert different things through heat. So it's a very valuable tool for that. Now, what can that camera do? Right? It has its limitations, as I said. It looks at surface temperature. Okay? So if we compare these two images, this is a thermal image, right? This is a visible light image of the same thing. Now, that's my hand there, and I'm holding a sheet of plexiglass, or whatever, Lexan, whatever you want to call it. But when we look at the thermal side of that, we can see where that glass stops here, that plexiglass stops right here, because my hand is visible. And we see a temperature difference, the surface of my hand. But because that plexiglass is there, it is a different surface, and it blocks me being able to show you the temperature of all my 4 fingers behind that. So be very aware of that. It will not see through objects. When we see all this stuff in the movies where the guys are looking through the scopes, we've all seen that, right? They're looking at these people through a wall. No, that doesn't work. That's movie magic. Okay? This is not movie magic. We can't do that. And when it does that, it's looking at infrared waves. So thermal, if you see, is looking at that short wave, middle wave, and long wave infrared, which is a different wavelength than our visible light spectrum versus ultraviolet and X-rays. So it's different wavelengths of light. And that's how we pull, whoops, I better not stand in front of the speaker. That's not going to work well. That's how we get the temperature signatures. Okay? So this is a great comparator. This is center point on there, 37.4 degrees. Minimum is over here, 33.6, and maximum, my wrist is pretty warm at 84 degrees.
Don't you have heating in your house?
Not in this part.
Okay.
This right now is my soon-to-be office that is not quite yet heated. Yeah, it was a little chilly when I took this picture, but I wanted to do that on purpose because one of the challenges with thermal cameras is you have to have a temperature differential. If all of these surfaces had been in the 80-degree range, I would have had a really hard time making that temperature differential show up in my picture unless I had set the camera up right. And we're going to talk more about that as we go through. Okay? So let's get into doing a little bit of inspection with IR, or infrared, thermal imaging, an IR camera, thermal camera. It's all this different terms for the same process. All right? So one of the first things we need to do is make sure we can do this stuff safely. If we're going to be using it, especially on equipment, we need to be able to do it safely. And as you'll see in here, there's different places you can use this, but all of these or most cameras you'll find are going to have a standard tripod spot on the end. Well, then, if I take that camera, say I want to look inside of a piece of equipment, or I need to look at a moving, we'll say a belt and a pulley inside of a blower, but it's inside of a cabinet, so I need to have that cabinet closed. Well, now I can take that camera and I can set that camera inside on a tripod or a magnet or whatever, and I can have my phone or my tablet outside the box, and I can watch that image on my phone or my iPad. Now I can get a good view thermally of what's going on inside a cabinet with the cabinet closed. I don't have to be sticking things in there. It's under normal operation, and I'm safe because I'm not sticking my hand or things like that inside that equipment. Wireless technology is an awesome friend for safety. And trust me, some of this stuff you don't want to get your hands into. Electrical cabinets, same thing. If you need to inspect something with the door closed for safety reasons, use that magnet, use a tripod, something inside of there. We need to understand what the surfaces are that we're measuring in the image. As you're going to see as we go through here, different surfaces respond differently and tell us different things. So you'll see that some as we go through, and we'll talk about some of the different surfaces, how to correct for different surfaces. You want to set the span and the level. Some new terminology maybe. We'll get to that in a minute. But we want to make sure that we understand how we're setting up the span and the level, whether it's doing it automatically or whether we are controlling the span and the level. It's a good idea to make a path up in your head before you start a process. Pick a beginning, pick an end, work side to side, up or down, whatever, because if you're taking images or anything like that, that way if you're thinking about it later or you're making notes, it's in order, it makes it nice and easy, and you don't miss something.
Because oftentimes the visual world and the thermal world look totally different
Very
because
different.
of that spectrum difference there. So I have a friend who's an energy auditor, and he does thermal image air sealing with enhanced by a blower door. He always takes right turns. So we always know if he goes back to, if he's developed a pattern, he always takes right turns, so he knows as he's moving through a house or a building or a structure, it's always the same pattern.
Mm-hmm. Yeah, and you can do that with equipment, houses, whatever you're doing. And it just makes sense, and like Bill said, that way you kind of know what you did automatically. And if you get in a sequence of following that same pattern every time, it's easy. Yep. Understand the equipment that you're looking at. Understand, and this goes back, you're going to have to practice some with this, or you're going to have to find some knowledge about that equipment. What should it look like when it's operating normally? And is what you're looking at on the screen not normal? This was a mistake that I made early on when I got my first camera. I called up Eric over at TrueTech, and I'm like, hey, I want a thermal camera. I've read about them. I've seen them. I think this is useful. At the time I was still in the field, I was a commercial technician. And I was like, hey, I've got all these units. I can use this. This is great. I'm here to tell you I made a lot of mistakes on reading those images. And this is one of the things, when you start reading images, and even after you get better at reading images, it's a good idea because, as Bill said, it's like a highlighter. It'll highlight areas. Then you need to take another tool to confirm that area is a problem. Double check yourself, right? Use multiple things. And we should be doing this in a lot of cases when we get into something. Double check as to see what the actual problem is, especially if you're trying to tell a customer, hey, this is broken. You have to spend money to fix this. You don't want to rely just on one thing. You want to have a couple different data points to be able to say this really is the problem and this is really how we're going to fix it. Or maybe there's more problems than you might think, and you dig into it a little deeper. So understand the equipment that you're measuring. Verify the problem areas, okay? And this is another big one, and we'll show you this in a little bit. Focus the image. And different cameras, like if you have one of these cameras, this camera doesn't have a focus on it, okay? But if you look at that camera in Bill's hand, it's a bigger camera, it's got better resolution, it has more pixels on it, it has a focus ring on it, kind of like an old camera or a fancy SLR or a bigger digital camera, and it changes the way the image looks. And you'll see that here in some of the upcoming images, all right, about and why do you want to do that? Because it changes how the software interprets the temperature on the screen. Right? Now, you want to have that baseline. Again, that goes back to kind of knowing that equipment. You want to know if we're looking at a piece of equipment and you're going through and troubleshooting it, you need to know the sequence of operations about how it's supposed to work before you can tell what's not working. So that's kind of like having that sequence of operations. That's your baseline. All right. Now, I mentioned something in there called level and span. Now, level and span. Levels are up here on this. Now, this is a screenshot of the screen actually on one of those cameras right there, okay? And the level and span is over on the right side. The level, this is your upper range of the color palette on that screen, and this is the lower range. So this one right now is set at 87.2 to 84.2, and the span is the differential between those two.
And anything above 87.2 is always going to look the same color going up. Anything lower than 84.2 will look the same color going down. So you've decided on the target area, the target temperature area of interest when you set this up.
Correct. Yeah, that's a great way of putting it. I like that. So you'll see in this one, okay, this is my visible picture. So I took a visible picture. This is concrete. You can see my shadow over here. This is actually a piece of sheet metal laying on my driveway in the sun. So the sun's coming at it this way, and the sun's to my back. It's a piece of sheet metal. We'll get a little bit more into what we're looking at right there later on. Now this is when that auto-ranged. Okay, so it automatically set that level and span. My maximum on that, in that picture, you'll find the max is at 46.4 degrees. All right, and my minimum is less than 22 degrees, and these are all in Fahrenheit. So it's less than 22 degrees Fahrenheit. And then I've got a couple spots on here as well, which we'll talk a little bit more about that later on in another slide when we start talking more about surfaces. But what I did is I took this picture and I changed the scale on it. I changed that span and I changed the levels so that now you can actually see my shadow on the concrete while I'm standing there.
The thermal impact of his shadow, not the light impact of his shadow.
Correct. Yes. Thank you. That's the thermal impact of that shadow is cooling the concrete down. So you can see the P1 and P2 temperatures in here. The P1 is 31.1, the P2 is 32.2. Just that distance apart. So there's about a 1.1 degree of thermal impact of me standing in the sunlight on that concrete right there.
And is it the aggregate in the driveway there? You're actually looking at the difference in the materials of the driveway, how they're absorbing and re-radiating infrared energy. That's why you see the spots. It's not a funky image, it's reality.
Yeah.
Those points actually have different temperatures to them.
Yeah. So you'll see all these different spots and things on here and how they work, and how where this metal sets on there affects how. Some of that is how the camera sees it, and some of it is how it actually affects the surface temperature of that concrete because that object is setting on it.
Yeah, it's starting to warm the concrete.
Yeah, so that just the solar effect off of that is actually starting to warm the concrete, even though the metal appears to be very cold. The metal is our coldest spot on there, right? Why is that?
It's emissivity. It's reflecting wrong.
Emissivity is a good portion of it, yeah. So, and everybody hear that, emissivity. Right? There's a new term. We're going to learn about emissivity a little bit later on. But what this is doing, because of the angle I'm at, I'm actually trying to read the temperature of the sky. Now, how cold is the sky? It's freaking cold. All right, we don't have coats for that, especially not here. This is Florida. But it's trying to read the temperature of the sky, which is why it's less than minus 22 degrees, because it's reflecting back up and trying to read the temperature of the sky. This is part of knowing the material that you're looking at. Right? And we can actually recreate this. I have the stuff out here. We'll talk about demonstrations and stuff later. And we're probably going to do some demonstrations on Saturday afternoon. There's some time for that.
Yep.
So we'll be able to do some demonstrations. I have the stuff to recreate this. If you want to recreate this experiment, we can take it out in the parking lot, and I'll show you how to do that and how it bounces, and you can see it for yourself.
And there's a couple other factors here that are built in. You got to look at sources of heat that may affect your image, especially over time, heat retention. So it's not like taking a measurement of a box. That's going to stay the same all the time. These kind of measurements can change over time, change with their exposure to heat sources. So we're not trying to make it complicated, but it is kind of intense. And you need to know these things before you go off and say, hey, I know what's going on.
Yeah, it's a whole different world. That was my introduction to this when I started playing with it. I quickly realized that I didn't quite know enough to really use it yet. And there was at the time a free course available online. Unfortunately, I can't direct you to that anymore because it's not there. But now, here's the focus. Okay, so this is the same sheet of metal that we just looked at laying out there on the driveway. This is a nice sharp focus, just like it would be in a visible light image, where we've got nice edges around here, and this one's way out of focus. Now the reason I want to point out focus is the one thing that you cannot change in software. If I take an out of focus image, it's always going to be out of focus. All this other stuff, all these spots, I can change the color palettes. I can change all the other things about that image except for the focus, because that's already stored. So make sure that when you get an image that it is well focused. Or if you want an out of focus image, take an out of focus image, because you'll notice that that looks very different between those two. And your temperature spots are going to change a lot, because I couldn't even get a P1 temperature if that's out of focus. Right?
And this P1, P2, P3 is as a feature in this kind of camera. You won't find that in every kind of camera going up and down, sort of the hierarchy of different cameras.
So these spots actually came in through the software.
Okay.
So
Post-processing.
It's called post-image processing. You take the image and then you draw it into a computer, or you can do some on your phone as well, or tablets, and you do post-image processing and editing in there where you can look at high and low temperature. And I'm going to show you a little bit more about that because the software is really, really powerful once you get started into it. So now, electrical connections. How many of us deal with electrical connections in here? Okay, if you don't, you're probably not going to be in this room very often. Some of us in here probably don't. But electrical connections are a really, really big thing. And you can see heat in them, okay? We've got several different kinds of images up here. Like this is what's called a fusion image. Okay, this is more of a thermal. It's a little bit of a fusion. That one's just a straight up thermal image. Okay, and we're going to talk about what those mean. But what I want to point out to you, we see a lot of heat. We see it back in this wire. But if I look at this thermal image, would any of you say that these are problems? Yes. Okay. Would you say that this is a problem? Yes. Now, I'm going to say that these down here may or may not be a problem. We don't know because I don't know how or the area that this image was taken in. All right? This is definitely a problem because I've got heat extending down a wire. This is affecting the insulation, which means it's going to be affecting the composition of actually the copper in the wire or whatever it's made out of, if it's aluminum, whatever. These, maybe, maybe not. When we saw that image of the metal, right, and I'm measuring the sky, what happens if I'm standing directly in front of this contactor and there is a heat source, and I'm standing in front of that contactor with my camera, and there's a heat source on either side of me behind that. And this is shiny metal right here. It could be picking up the heat source behind me. And I could be looking at this going, hey, this is a problem, we got to replace this, when all I need to do is tighten up or fix a connection up here on this. So you've got to know the environment. We're going to look a little bit more of that as we go on.
So he asked, besides the connection, what else can cause that on the connector?
So loose connection up here, these down here, if those are truly hot spots, and how I would find that is I would move side to side a little bit with my camera to see if I'm blocking something. I see how that image changes. That may be pitted or burned contacts on your contactor.
So he's creating a thermal shadow so he can inspect the equipment.
Yeah. So
You can also be the heat source that's being reflected.
that is correct. You
Yeah.
can also be the heat source that is reflected. Absolutely. If you play with a thermal camera and you walk, one of the first things that you should play with is walk up to a plate glass door. You know, sliding glass door, big window, whatever you want to do, and wave at yourself in the image because you'll get to see yourself.
Because glass is a thermal mirror.
Yeah.
You know, silver mirrors are visual mirrors to us. Glass is a thermal mirror. Would
Would I
oxidization
see
cause
this
that?
with oxidization? Yes, potentially. Yeah. This is some examples of the different images. All right. So this is a thermal image. All right. This is a visible image, and that is a fusion image. All of the same space. Now, if you look closely in here, you'll notice there's a column right here, and this is actually a glass wall. So when that image was taken, these people, which appear to be standing there, are not really standing there. Their heat is being reflected in that glass wall. So it looks like they're standing in the room. And this is one reason why visible images are so important to correlate to thermal images, because like Bill pointed out earlier, if you look at this image alone, why the heck are there people standing there? Well, there weren't, right? But I can't see the heat signatures of all that stuff behind that glass because the glass is in the way and it's showing me what's behind here. Okay? So thermal, visible, fusion takes the visible and the thermal and melds them together for better identification later, so that if I'm going back maybe a week, a month, or you take that picture and you send it to somebody and you say, here's the problem, this is where you need to focus on, now they can identify it.
What do we think's going on here with this guy's face? Yeah, he's got cold eyes or he's got glasses. So.
There you go.
Yeah.
Good. So that's all part of analysis of that image, right? Now this up here is what we call a picture-in-picture. So we take the larger visible image and we have a smaller thermal image in the middle of it, and that gives us, again, an idea of location, but we get that really solid thermal image versus that fusion can kind of look a little strange sometimes. And one of the other challenges with the thermal versus the fusion image, it needs to be a good distance, taken a good distance away, because if I look at, that camera's got it on it. This camera does not have, this only does thermal images. This does not do thermal and visual images. Whereas this camera, if you look at the front of it, there are two separate lenses. The visible lens is up here and the thermal lens is down here. So they're coming out at two different angles. So they don't always align. And the closer you get to something, the worse that misalignment becomes. So the farther away you get, the better that alignment typically is. Right? If you try to zoom up real close or you want to get a foot away from something, you're not going to get a good thermal and visual image alignment. You can take them, but it's going to look really wonky when you try to put them together and you try to actually pinpoint a spot. So that's where your picture-in-picture comes in. Depends on what you're trying to do. Now here's what we're talking about, these reflected heat signatures. So if I have a camera, I'm looking at this area here, and I have a heat source over here, it's going to bounce up and reflect back into that lens. This is going to appear to be a hot spot. This is actually hot, this surface isn't, because we're radiating heat. Remember, this measures heat, so radiant heat will bounce.
So think of that like the person standing in front of the glass.
Person standing in front of the glass. Or how many of us have walked out in the summertime with a big sheet of sheet metal or ductwork and you felt that heat coming up off of you? Or how many are old enough in here to remember Radar in MASH sitting there with his sunshade getting a tan in front of Colonel Potter's office?
Yeah.
Right?
Apparently not enough.
Not enough of them, apparently, yeah. It's a good show. You should watch it anyway. You can get it. Again, same thing. You can get very shallow angles as well. And this becomes an issue when you're looking in houses and things like that, where you're looking at the side. You need to try to be as straight on as possible, but you've got to be aware of what's in the reflection zone. This becomes an issue when measuring pipe temperature. If you're trying to measure pipe temperature, because we all work with pipes and refrigerant and things like that, and water and all this stuff, if you have a really shiny surface on that pipe or a very reflective surface on that pipe and you have a heat signature over here, you're only going to be able to get a really small spot that's actually an accurate temperature. And that's why we say this is a comparator. It is not an active measurement tool. It's a comparison tool between two different surfaces that are in the same image or in the same span range. If you have your level and span set the same and you look at two different objects and you can compare those two different objects, but they're not in the same image. All right? But they have to have the same surface characteristics.
And if you're aware of something that's going to cause this kind of issue, you can put a material in between that is not going to allow that thermal energy to reach the pipe or whatever your object of interest in. And surprisingly, garbage bags work great. So it's a real cheap solution to sort of like, if this is a critical thing, just kind of drape the area, and you can nullify or filter out
a lot of stuff.
A lot of the reflected energy.
Cardboard or plastic is better?
What I've heard is polyfilm, garbage bags are better. I think cardboard might have a little bit of thermal mass that could then heat and then reflect more. So, and it's easier to bring a garbage bag than a big piece of cardboard. But yeah, good point.
Yeah, if the cardboard has a thermal mass on it, it's going to do the same. It's going to act as the same thing as this. Yeah. Where the garbage bag probably doesn't have a lot of thermal mass to it, and it's also a different surface characteristics where it's not going to add heat to that, if that makes sense. So we were talking a little bit, and we kind of already touched on this, on the reflected heat and about how that reflects off of surfaces, right? And we're going to touch a little bit more on this as we get going, but if I want an actual measurement of that piece of metal, I put a target spot on there with what's called what's called emissivity. And that tells us how that surface radiates heat back to the sensor. So I know about what the emissivity of this is, and when I put that P1 spot, or I could move my center spot over there if I aim my camera right on that center spot, and I can tell that the temperature, the actual temperature of that metal is about 33.1 degrees. Because I set that spot up on there manually with the software after in editing. We'll talk about that. So this is a really important thing to understand. Qualitative versus quantitative. And I'm going to give this one to Bill because he's standing over there chomping at the bit to teach something.
Sure. So qualitative is you're looking for these differences. You're looking for it to be a filter or screening aspect. Again, looking for the abnormalities, like what's wrong with this picture. And that can help you quickly scan a scene. Quantitative is more precise measurements. Then you have to be concerned with the emissivity. You have to be concerned with reflected sources. A lot of times for our work, when you're troubleshooting, trying to find areas either in the building structure or equipment, you just need a hint as to where to go, where to start, where to move. So be careful if you get into quantitative measurements, because you're going to need to know a lot of other factors to be really definitive about those quantitative measurements. And there's tables of emissivity for all kinds of surfaces, but the higher you are to 1, the more you're looking at what that surface is emitting. So a perfect black body radiator is an emissivity of 1. Fortunately, things like drywall, most building materials are around 0.9 to 0.94. So you're in that range where they're mostly going to be emitting the energy and not reflecting it. But when you get into materials like metal piping, aluminum, copper, they're going to be doing a lot of reflecting. So they're going to be picking up all kinds of other stray signals, which aren't going to allow you to make those definitive temperature measurements.
Yeah, so that's why we have that note in there. You really want that surface to be above a 0.9 if you're going to try to do a quantitative measurement. Okay, 99% of what we do is going to be that qualitative. So, but keep that in mind when you're taking these temperature readings and you're looking at this stuff. Okay.
So what do you think sheet metal is? Do you think it's low or high emissivity? Right, okay, so you get this. Right.
All right. So that's what emissivity is and it's compared to a black body. You want to take this?
Go ahead.
Go for it. So the emissivity numbers that we see of something we're measuring is compared to the radiation capability of a perfect black body. And that means it radiates everything in infrared energy out of it. And that uses a scale of 0.0 to 1.0. 1.0 being that perfect black body and 0.0 being super reflective. Most cameras are going to come set up in that 0.95 to 0.97 range preset from the factory. That's where they're going to be automatic at. But you can go in and adjust them depending on what kind of material. If you need a better quantitative measurement, a more accurate measurement on there, you want to be a little more precise, go in and adjust that. And you can find emissivity tables online. I don't have any to just give you right now, but find them online. They're readily available. They're downloadable in a PDF. Free for everybody out there. We talked about targets, and as I told you, I put a target on here. And there's some really common, easy to use stuff that we have around every day, right? 3M electrical tape, 33 plus electrical tape, or most black electrical tapes is around a 0.97 emissivity. So it's a pretty good thing. We can stick that on a lot of stuff and get pretty doggone accurate measurements off of it. All right. Testo makes an emission tape. That's the part number for it. It's honking expensive if you want to buy it, but it is out there, and it's a 0.95. It's going to be dead on that. Masking tape, I'm told, is a 0.92, but there's some issues with masking tape. And it comes up on the emissivity tables as roughly a 0.92, but you have to be careful about what sort of a surface you're putting on, and I'll show that to you in the demonstration. If you come out to the demo on Saturday, it has some interesting characteristics where if it's backlit, it will actually not work properly because of how much light it passes through it. So it lets you see a little bit of the surface behind it, if it's glass or a really shiny surface behind it. Kind of an interesting characteristic I uncovered doing some stuff.
And keep in mind, when you add tape like this, it's a hack, and sometimes hacks comes with downsides. In this case, you're now reading the temperature of the tape that's on the metal.
Yeah.
So in as much as that metal can either draw or represent its temperature to the surface of the tape, if it was something really tiny, like a nut, and you put a piece of tape on it, you just messed it all up. Now you don't know what you're reading. So something of larger thermal mass with a small amount of tape that's a smaller thermal mass, and then you enter the ballpark of getting a realistic measurement.
So if you want to measure a pipe temperature or a window glass temperature or something like that, that's a really good place to use that electrical tape or emission tape. Again, the masking tape, I put it on here because it's listed as that 0.92, but I wouldn't actually recommend it because of how it responds to, and it allows that surface behind it to affect the reading in some ways. Okay? Motors is a great place. So we're going to talk a little bit more about things you can use this on. Motors is a great one. Now this is a great image, and I love this image right here, and we're going to talk a little bit more about this. What do you notice about that image right there? Okay, there's 4 fans, so that's a qualitative or quantitative measurement? Qualitative? Quantitative?
Oh, this picture?
Yeah.
Oh, it's qualitative.
Yeah, qualitative, because we're comparing this to the other 3 fans, and we're saying this one's running hot. So you need to know, is this the only fan running? Or are there bearings going bad in it, or something, probably bearings going bad in that. So if it's the only fan running, of course it should be hotter than the rest. But if all 4 fans are running, and that's the one that's reading that temperature, I got a motor problem, I better get that motor changed out if I want this piece of equipment to be continuing to operate.
Another example would be I had a friend who was remodeling a house, a little lake house, and walked around with a thermal imager before he had any insulation in the walls. And he said, wow, this is great, because it's not showing any thermal defects. It's because it was the outdoor temperature. So he wasn't really trying to hold any heat in or keep any heat from leaving. It was, you got to know more background. Use your technical mind to ask these kind of questions.
Is that our mutual friend? Because I think I know who you're talking about
it
there.
was.
Yeah, okay. We're not throwing anybody under the bus here.
No. We're getting them near the wheels, but not under the bus.
It's a learning curve, right? Okay? We don't know it until we don't know it. Until we realize we needed to know it afterwards, right? Because if you don't know something and you don't know you need to know something, how do you learn it?
What you don't know, you don't even know that you didn't know about it.
Exactly. And I'm not even going to try to you're going to repeat that one?
What you don't know, you didn't even know that you don't know about it.
There you go. See? Okay. One of the things I wanted to point out about this is kind of the pixelation in here, because I blew this image up a lot, but you see that pixelation in there. And all of these cameras have a resolution, and we'll talk a little bit more about resolution, but I want you to see what happens if you blow up kind of a lower, and even a high resolution camera, if you expand it far enough, it's going to pixelate at some point. But the lower the resolution, if you think you need to blow stuff up to get really fine detail, you got to make sure you're looking at higher resolution camera. Now, palette. Now this is something that I haven't really talked about yet, but it's important because if you look over here, remember we talked about that level and span on the right-hand side, you'll notice that each one of these is what we call different color palette now. So your hot and colds change depending on what color palette you select. And some of this helps with interpretation, but some of it also is if you're going to ship stuff to a customer, you may want to select a color palette that, because they don't understand reading a thermal image, you kind of want to bring something that's automatically makes sense to them. Like this one right here where blue is colder, white is hotter, you know, red to white, and yellow's kind of in the middle. Well, that makes sense to somebody who's never looked at, doesn't understand. But if you handed them like this one and purple is colder than blue, right, that may be a little weird, and green is in the middle. Or if you look at this one over here where it's black is cold and white is hot, well, what the heck is that? We don't know. It's all about the interpretation. So there's different ones that can help different ways. Now, selecting that deeper in, it's a little bit more than what we're going to get into in the class, but I wanted to point that out to you. All right, compressors is another great use application for this, especially on semi-hermetic compressors if you need to diagnose things, but even on hermetic compressors. There's all kinds of different things you can look at on the outside of that. If you look on the body of like a hermetic compressor, you can see if there is hot gas bypassing internally back into the suction, because you're going to see a warmer spot on that outside case down there. If you're looking at the semi-hermetics here, you can find bad valves. You can find out if unloaders are working. You can find out all kinds of stuff because you can see how that refrigerant flows through the heads. You can watch it all happen with a thermal camera. So it's very, very useful for any kind of compressor work. I love it.
Keep in mind what you're seeing is the effect on the surface of things going on under the surface.
Right. You're watching that temperature change as the refrigerant moves through the compressor and different things open up. Unloaders turn different things on and off inside the compressor.
So this is like a highlight upon like a compressor teardown video. If you watch one of those, if you know what's going on inside, it can help you with interpretation of what's going on outside.
Mm-hmm.
Is that a fusion image, that one?
That one looks like pretty much a thermal image there.
Yeah, only thermal.
Yeah, I would say. It might, I don't know, there might be a little fusion in here, but I would say that's mostly thermal. Yeah. And there's gradients that you can change the fusion. So there's, on the program, there's like a slider bar, and you can slide it more towards visual or more towards thermal. So I would say that one's almost 100% thermal, if not 100% thermal. This is a misaligned belt. Anybody in here work with systems with belts on them? Right? So when that belt gets misaligned, it starts rubbing on the side of the sheave or the pulley, and it creates heat. Well, guess what you can see with a thermal camera? You can see that heat being generated. So this is a really great, and this is where I mentioned putting these things inside of equipment and watching it wirelessly. Now I can put that in there and step back and watch it from across the room where I'm operating the equipment, but I can see that I've got a misaligned belt, and I can visually show that that belt is getting too hot. It's getting hotter than it should be. Right? And I can show that. I can show that that sheave is going to have more wear on one side of it or the other side of it. And it's preventative maintenance. Right? It's showing that there's a problem visually rather than just walking up and saying, hey, Mr. Customer, your belt's out of alignment, so it needs to be fixed. Well, why? They don't know why. They're like, my air conditioning's still running. No, it's getting hot. Here, I can show you an image of it. Bearings. It's a cool one where you can watch if you find a hot bearing, or you shoot something and you find a bearing that you think is a little warmer, and then sit there and maybe put it on video record mode or have it set up and watch when you pump grease into it, and just watch that temperature of that bearing drop down because you're removing the friction from it. And it'll gradually cool the whole thing down. It's kind of a neat thing to me because on bearings, if you've ever done much work or studied greasing and lubricating bearings, over-lubricating is sometimes just as bad or worse than under-lubricating a bearing. And this was something I had never thought of in the field, and I wish I had my thermal camera and had done a lot more with it, because I probably would have done a lot more lubrication based on the thermal temperature of the bearings rather than just randomly pumping grease into them. And not over lubricating bearings, because that will kill bearings because it blows the seals out of them, and then you get all kinds of dirt in them real fast if you've done that much. Hot components. Okay, this was they're actually observing a weld cooling pattern on this one. But think about how many times we got something hot and we walk up and we're like, oh, is this hot enough to touch? Or I can grab this and go, yeah, I'm not touching that yet. and save your fingerprints if you like to do that.
So we have 5 minutes.
We have 5 minutes?
We have 5 minutes.
Wow. Okay, we better keep going.
Yeah.
All right. So we haven't even gotten into buildings yet.
No, we
Holy
haven't.
cow.
Yeah.
All right. So some other components.
You know what? We're going to do a webinar on this, right?
We are going to do a webinar
And it's going to be a video on the True Tech channel, so you can get the full-blown feature, which you can't get here because of time compression.
Yeah.
Keep going.
So just some other components real quick, but basically it comes down to anything that you can troubleshoot with a surface temperature. Comparative-wise, you can use one of these cameras on. Now, let's talk real quick about inspecting some structures. Okay? Here's some tips for you.
And you can kind of summarize them. Know heat sources. Know the time this has happened over. The time is important because of thermal mass. Things gain and lose heat. Know what your heat sources are, including the sun. That's also another source of heat.
Big source of heat. Yeah. And you want to have a sufficient temperature differential between indoors and outdoors. Because if your inside is 75 degrees and your outside is 75 degrees, you're not going to have a temperature differential. The bigger the temperature differential, the easier it is to see the problems. But that's also where your level and span can come in. So if you have a smaller temperature differential, then you've got to start bringing the levels and the span closer together and more into line to be able to find issues. All right? So you can find air leakage. That's an outlet, right? Well, that's cold air actually blowing through that outlet. So you can visually see that. Airflow patterns. Now, again, this is leakage, but another thing I find really useful because I do some home testing is I can now visualize the airflow patterns of the HVAC system on the surfaces in the room. Because surface temperature control is very important. So now I can visualize that real fast and easily. I can look at mean radiant temperature. Now this, obviously there's some insulation missing in those cavities up there, but mean radiant temperature is the average temperature of all those surfaces in that room that affect me because I'm constantly radiating heat. And if those surfaces are too cold, I lose a lot more heat, but if they're too hot, I can't lose enough heat and I overheat. So this is where human temperature control comes in too. So when you start visualizing mean radiant temperature, if you use your level and span and you want your mean radiant to be really close to what the thermostat set point is. So if you set your level and span at like that plus or minus 2 to 5 degrees of the thermostat, now you can start going around and visualizing where the hot and cold spots are in a space.
It's kind of like asking the building, okay, who's the troublemaker here? You know,
right.
What's causing the issue? Now you can home in on the issue.
Mm-hmm. So if Mrs. Jones is, I sit in my chair and I'm cold. Well, yeah, this wall behind you has no insulation in it. Of course you're going to be cold. Doesn't matter how much hot air we blow on this side's going to be cold. Okay? Visualizing mean radiant. This one's a little hard to see on here, unfortunately. But what this tells me in the software, I put a box on here, and it will tell me over here what percentage of what temperature is inside that box, and it gives me an average temperature of that entire box. So my average temperature, or mean radiant, of this box is 64 degrees, but of the whole image is 65.5. This is another place the software becomes really useful because you can't do that on the camera. They're two different tools, but you use them together. Now this is your thermal mass.
Right. So
this is the back of a house.
Okay.
After the sun went down, about 20 minutes after the sun set, right? So you see, up here you see a spotlight, really warm. But down here, that whole wall's cooled off. We can see a little bit of a heat signature actually coming from the attic because the attic is still hot. But what do you think all this is down here? Concrete wall. It holds heat. It retains heat. So knowing that that sun just set, this is not a problem because that's concrete. It should be retaining heat. All of this up here is vinyl siding. It has let its heat go already. And we are getting the stop sign.
Wow.
All right. So we're going to be at the booth
Yes.
all week. If you got more questions, stop by and ask us. Wish we could have got through everything.
Yeah, and we'll do a webinar on this and a video.
Yep.
So you can
and
get the full
come
dose.
out on Saturday afternoon, and we'll be doing some demos out in the
hands-on.
parking lot.
Thank you for your time and attention.
Thank you.
Big thanks to Eric. Big thanks to Bill. Big thanks to TruTech Tools. As always, to get a great discount at checkout at TruTechTools.com, use the offer code GetSchooled. That is our offer code. I buy a ton of tools from TruTech Tools, and when I do it, that's how I do it. I just go to TruTech Tools. I use my own offer code, and that's how we do it. I don't get anything from that offer code. It's just a great discount that I want to pass along to you for helping the community. So once again, big thanks to Bill. Big thanks to Eric. Big thanks to TruTech. And watch out at HVACRschool.com/symposium for next year's symposium. You're going to want to sign up early because it's going to sell out quick when tickets go on sale. Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to HVACRschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.